Good, welcome back. It is my great honor to welcome Christopher Fuchs today as our first tandem speaker of the symposium. So just to clarify things from the very beginning. So in case you ever read Asterix in Corsica, there is this running gag of a vendetta between two families. The only thing people remember is that it has to do with a mule, but so with a donkey. But actually, no one in the whole family over generations remember what the actual story was. And in a way, it turns out that Chris and I promise to each other, and that whenever there's going to be an occasion where we both are at the podium, we will both wear lederhosen. We don't remember, none of us, when this promise was made or why it was made.
A sign that alcohol was involved.
We just remembered that it was made. And so today, actually, we fulfill this promise. And I have to say, Chris, you look very Bavarian. So let's get back to business. So Chris is a professor of physics at the University of Massachusetts in Boston. He obtained his PhD back at the times with Carl Caves at the University of New Mexico, already related to quantum measurements. After that, he toured the world, so to speak. He was recipient of a prize fellowship that led him to Caltech as a postdoc. Then he had positions at Bell Labs, at Perimeter Institute. There was also an episode at BBN Technologies. He was a research fellow at the Max-Planck-Institute for Quantum Optics in Garching, and eventually is now faculty at the University of Massachusetts. Chris has several noteworthy distinctions. He was recipient of the Quantum Communication Award. He is a fellow of the American Physical Society, and he is also a very gifted philosopher and writer. With that, I hand over the microphone to Chris. We very much look forward to hearing the introduction into the tandem talks. Chris, stage is yours.
Thank you.
Thanks for being here.
And thank you for wearing the lederhosen. I was genuinely afraid this morning as I spent the necessary 20 or 30 minutes it took to get this on, that Professor Aspelmeyer would come and wouldn't be wearing his lederhosen, then I would be the only fool out here. So let me just say that Professor Aspelmeyer is now the director of IQOQI, I believe. But let me tell you about when I met him. It was in 2004 at a meeting called Seven Pines, and he was substituting for Anton Zeilinger. Anton Zeilinger had been invited to give a talk, and I guess he couldn't come. And Marcus Aspelmeyer came. He was a very young man. He had this enormous hair. He looked like one of the great symphonists from Vienna at the time. And he got up to give a talk without Anton Zeilinger's reputation. And so there he was in front of a number of great physicists, Robert Wald, I remember, and John Preskill, and a lot of people with great reputation. And Marcus stands up and boldly claims that we learn a lesson from quantum theory. There is no reality. And he said it very confidently. There is no reality, and that's what we've learned. And you know, he was all of 15 or 18 years old. And I was in the audience cringing because I had a kind of, I enjoyed his company. And I thought, you know, you can't say that yet. Anton might be able to say that, but you can't say that yet. poor boy, his career won't go anywhere. Anyway, in a way, that story, I think, captures a bit of what I'm hoping to convey to you today about the interplay between things in our field and the, well, you'll see. You'll see. Oh, you know, I was told that it was put there so that I wouldn't be turning around here. Anyway, here it is. So I have a habit of telling stories. One collection of my stories is in this Cambridge University Press book, Coming of Age with Quantum Information. If I get through my whole talk, I'll tell you 2 stories today. I have promised the organizers that I wouldn't talk about my usual subject, which is a point of view on quantum theory that I've developed with Rudiger Schock and Carlton Caves and David Merman. I think basically the message I got from Flavio was that I talk on cubism, and then I always talk on cubism and cubism and cubism. And he wanted something different for today. I think an appropriate topic is what I call the mad rush for quantum computing. You especially see it in the United States. We now have something called the National Quantum Initiative. It's a huge pot of money, and many universities are trying to get hold of some of this money by developing teams that work on making genuine quantum computers. It's also happening in China, where there's an even bigger pot of money. I've heard that the Chinese have put down something like the equivalent of $10 billion US to build a national laboratory for quantum information studies. In this mad rush for quantum computing, one over and over sees the students not knowing anything about the origins of the field. It's irrelevant to them. If you go up to someone working, just to give you some sense of this, IBM Research has probably 50 paid staff working in quantum computers now. Maybe it's even more than that. A number of years ago, it was 30, and I'm just extrapolating that it might well be 50. If you go up to most of these people and ask, do you know about quantum teleportation? They say it's an important protocol in building quantum computers. Do you know why people ask the question, quantum teleportation? No, they have no idea. Do you know who discovered quantum teleportation? They have no idea. Do you know why the notion of qubit was invented? And who invented the name qubit? They have no idea. Qubits are just components in quantum computers. They've forgotten that there were actual questions that led to these things. Qubits weren't always here. In fact, before 1991, the world had no qubits. The word had never been uttered. They don't know that Ben Schumacher, for instance, invented the idea for a reason and invented the name for a reason. So that kind of gives you a sense of the lay of the land as it is presently. But many of the things that have gone into quantum computing were genuinely motivated by foundational thinking and foundational research. And I decided for my talk today to give you at least a couple of my own stories of that ilk. I picked this up off of Google Scholar. It's the page on me, and it shows my 5 or so, my 5 top papers. These papers have some number of citations because they have been useful in quantum information theory. That's the only reason they have citations, or to any extent, is because they've been useful for quantum information theory. But I can tell you the truth, behind each of those papers was me quietly, secretly working in the closet on quantum foundational issues. And when an opportunity arose to put some foundational thinking into some kind of calculation or other, then I usually rose to the task. But though these are useful for quantum information, their origins are in foundational thinking. At least, I mean, all of these I say. In particular, I'm going to focus on this one, non-commuting mixed states cannot be broadcast, and tell you a little bit of the history. And then if I have time, there's one right below there that I couldn't get on the screen. So you see where my light is, that I'll also tell you about. Particularly, I want to tell you about the influence of these two men in my life and in the results that I'll tell you about. John Wheeler, I was fortunate enough to work on a senior thesis with him, or with his group, more carefully, not with him, but with his group in 1985-86 at the University of Texas. And then later I met this man, Asher Perez. Both of these guys, the people at IBM wouldn't know it, but both of these guys were influential on what came to be the field of quantum information. My interaction with Wheeler actually started, my interaction in my mind with Wheeler started when I was in junior high school. So that means I was around 12, 13, 14 years old, something like that. I had a serious interest in science fiction growing up. I only watched science fiction movies, and I didn't read much, so I didn't read much science fiction, but I watched lots of movies and television shows, like the television show Star Trek. And I was quite taken with the idea of flying to the stars. And being brash in junior high school, I thought, if we're going to fly to the stars, then we've got to get to work. We've got to find a way to do it. So I started reading everything that I could about physics and about relativity and about wormholes and black holes and so forth. And that was my first introduction to John Archibald Wheeler. But the more I read, the more I became depressed, because I learned that there's this thing called the speed of light, and it's the speed limit, and it looks like physics would block our getting to the stars. By the way, I'm telling you a story now that I did not realize until maybe 10 years ago. I hadn't realized that there was a causal chain from my childhood to where I am. So I haven't always known this story. It only dawned on me at a lunchtime conversation with another historian, or a popularizer of science, Hans Christian von Baer. I was just recounting things, and this came to my mind. Laws of physics wouldn't allow us to get to the stars. And this started nagging at me. And I would jokingly tell my friends that if the laws of physics won't allow us to get to the stars, then the laws of physics have to be wrong. And I think I kind of meant it. I mean, it was a bit of a joke, but I thought, well, they've just got to be wrong, because physics, the world wouldn't be built in such a way that we can't get to the stars. So anyway, this was in the back of my mind, and I applied to a couple of places for college, one more prestigious and one less prestigious. One was the University of Texas at Austin, and I took a visit to Austin, and I found the table of reprints of John Wheeler as I walked by his office, and I picked up all the preprints, and they were all about the theme of law without law. Wheeler had this idea that I later wrote down in one of these memoirs as such. In those days, John walked around not saying it from bit. That came with a later turn of mind, but instead he would talk about law without law. As he put it, nature conserves nothing. This is a direct quote. Nature conserves nothing. There is no constant of physics that is not transcended. Mutability is a law of nature. The only law is that there is no law. And it all came together for me. If I were to study quantum theory, I thought at that time, I might just find a way to make my wish that the laws of physics are wrong, happen. John saw the quantum as a chink in the armor of law. It would take years for me to come to grips with the idea, but I found the thought so exciting, so alluring, almost as if it were made for me, that I couldn't keep my eyes off of it. That was my introduction to physics. I had read popular physics books. And then I found John Wheeler, and he seemed to be hinting that maybe there are no laws after all, and if there are no laws, then, well, then they were meant to be broken. And this really, really excited me. So I went toward a physics degree, not because I had this, oh, I want to understand the laws of nature, these beautiful, elegant things. I went into physics precisely to figure out what was up with quantum mechanics and whether Wheeler was right that quantum mechanics indicated that, in a certain sense, the world is lawless. So I endured a physics degree. I learned classical physics even though I hated classical physics. I learned classical electrodynamics even though I hated classical electrodynamics. The only thing I ever cared about was quantum theory, and even then, I hated perturbation theory. And I hated studying molecular levels. I hated all of that. All I wanted to do was quantum foundations. The other person in my story is Asher Perez, who I first met in 1993 when he was visiting University of New Mexico in Albuquerque. And Perez, I think I had already discovered him in print before in person, but he made a big impression on me in several ways. One was he was just a very funny old man who also wore funny old hats. And he carried a funny old umbrella that had tape. All the spots where it tore. He used the same umbrella for 25 years. Anyway, he was a wonderful character. And he was very difficult to talk to, so we emailed each other a lot. If we were in person, no conversation ever transpired. So in that time, I was trying to tell him about my research, and he would start to fall asleep. And he would say, I'm so very tired, perhaps write me about it. And so our relation was built that way. And then I gave a talk in 1994 at a meeting that was organized by Danny Greenberger in honor of John Wheeler. And I gave my first big talk in front of a big audience. And, I should tell you that at that time, Asher didn't want to talk about my research. He would say, yes, before getting tired, he'd say, yes, I have a student working on this. You should talk to my student. And he paid me no attention. And then at Danny's meeting, I gave a talk in front of this audience, and I showed some bounds on information that could be extracted by quantum measurements. And afterward, Asher came to me and said, you have done everything that my student has done and more. When I go home, I will tell him to stop working on this problem. So then I fell in love with Asher Perez, and we had a number of papers after that. One of the things the big thing that I draw here is his book. This book was influential in quantum information more generally because it was the first textbook that introduced ideas like entanglement and the Cauchy-Specker theorem and generalized quantum measurements and quantum logic gates. All of this was in this book. It was the very first book. So it was important for quantum information generally, but the big impression that it made on me is that over and over, Asher would compare non-orthogonal quantum states, pure quantum states. He would compare them to Liouville distributions in classical physics. And I took just a few passages here out of his chapter 3. Do I have a light? I think maybe the battery is dying, if not dead. Let's see if you can fix it. In any case, he says the generic case is a pair of state vectors. He's talking about state vectors here that are neither parallel nor orthogonal. This partial likeness being neither parallel nor orthogonal. The partial likeness he's talking about is not peculiar to quantum physics. In the classical phase space 2, we may have Liouville distributions, F1 of Q and P, the coordinates, and F2 of Q and P, which partly overlap. They may be disjoint, like in this case, or they may partly overlap, as shown in figure 3.1. Notice that this figure represents our imperfect knowledge of the classical Q and P of a single pendulum. The use of Liouville densities for representing this imperfect knowledge has the following meaning, and then he went on to elaborate. The point that Asher made over and over and over was that we should not compare state vectors, these objects that we talk about in quantum theory. We shouldn't compare those things to phase space points. So here's a state of reality in classical physics. It's the actual value of Q and P. And a quantum state, he would say, should not be compared to that. Rather, the quantum state should be compared to something like Liouville distribution. A quantum state should be compared to a state of imperfect knowledge. And then he gave examples in the book of where it was useful to think that way. And that was great. One of the key things that he pointed out was that if we take this point of view of quantum states, that they shouldn't be compared to the phase space point, but rather to imperfect knowledge about the phase space point, then some of these questions at the heart of the foundational debates just dissolved. So what makes a quantum state collapse? He would say, well, learning something makes it collapse because it's knowledge to begin with. Action at a distance, there is no action at a distance. I perform a measurement here, and I learned something about over there. Nothing happened over there. It all happened right here. So I had this point of view that if you took this as your picture, then those two questions were just smited. Is that a word? Smitten. Yeah, smitten. Well, smitten now sounds like, oh, you fell in love with it, but they were smote. Is that a word? They were knocked out. In this way, he agreed with Einstein, certainly. Here's a quote of Einstein from 1949. The spook of quantum mechanics disappears only if one relinquishes the orthodox standpoint according to which the psi function is accepted as a complete description of the single system. It may appear, I love the way he's apologetic just a bit, it may appear as if all such considerations were just superfluous, learned hair-splitting, which have nothing to do with physics proper. However, it depends precisely upon such considerations in which direction one believes one must look for the future conceptual basis of physics. I took that to heart, and I think I learned that from Asher Perez. It makes a difference how you think about these things, whether you compare this to that, the point, or whether you compare this to that. And making a decision in which line of thought you will pursue will mold what kinds of physics you pursue, what kinds of physical questions you pursue, and where it leads to in making advances in physics and potentially, say, to the subject of tomorrow's talks, in how you understand what quantum gravity is about. So I want to give you two examples of that. And let's see where it goes. The first one I want to talk about is something called the No-Cloning-Theorem. All of you, how many of you know about the No-Cloning-Theorem? Is this just a common knowledge thing here? That's wonderful. Good. So the No-Cloning-Theorem says you can't take a state that you don't know and build some device that will make 2 copies of the state. So you imagine some device, you throw in a quantum system for which there's a state psi. The device doesn't know what psi is. Maybe you don't know what psi is. You throw it into the system, and you want 2 quantum systems to come out with the same state that you threw in. Can you do that? And the no-cloning theorem says you can't do it. Most people know about the proof by Bill Wooters and Wojciech Zurek and John Wheeler. Here's John Wheeler in the middle. Here, this is Kip Thorne, by the way. And this is Bill Unruh, a young Bill Unruh, a much thinner Bill Unruh than we see presently today. This is John Wheeler. That was taken in 1981 in Bad Windsheim, I think is the name of the place. So 1 year before the no-cloning theorem. So this is what they looked like. But actually, Bill looks, well, they both look a lot alike still. The hair's a little grayer. Bill's hair is shorter. They had written this up. I hear Bill Wooters tell me it came about because he and Wojciech Zurek shared a hotel in San Antonio, Texas. That's the place where my story started because I watched science fiction movies from San Antonio, Texas. They were in a hotel in San Antonio, Texas. They had come upon this paper by Nick Herbert that David Kaiser might or might not talk about a little bit. And it purported to be able to signal superluminally. There's just one little catch. You had to have a device that would do this process. And I could tell you more about that. And maybe you know, come up to me, because I love to tell this story about the prehistory of the no-cloning theorem. But they had come across this paper. They were in a hotel together. And Bill says that they looked at the paper, and within 15 minutes, and he wasn't joking, within 15 minutes they showed why it was wrong. And it was because of the no-cloning theorem. And it doesn't take you more than 15 minutes to prove it. Anyway, they're most famous for discovering this. If you look on Google Scholar as of yesterday, there were 5,008 citations to that paper. But it shouldn't be forgotten that it was proven by some other people. One of them was Dennis Deeks in Utrecht. I should have mentioned here, I just started to mention, these guys wrote their first paper. They showed it to John Wheeler. They were going to submit it to American Journal of Physics, a teaching journal. And Wheeler said, no, this is too important. You should submit it to Nature. And you need a better title. And then Wheeler made up the title, A Single Quantum Cannot Be Cloned. And that was successful, as you see by the 5,008 citations. Dennis Deeks wrote a paper proving exactly the same theorem in exactly the same way. Hey, Denny.
The GHC paper we were going to publish in Phaidra, and we decided it was too important that we published it in American.
That is surely true. So Deeks wrote a paper that was titled something like Communication by EPR Devices. Consequently, poor Dennis is only recognized by 1,382 citations. A lot of people don't even know that he proved it. And very few people know that Giancarlo Ghirardi proved it himself. I know of only one citation to this, and that's in David Kaiser's book, How the Hippies Saved Physics. But I learned it from Ghirardi himself. Ghirardi was one of the referees of Nick Herbert's paper purporting to communicate superluminally, and he rejected the paper. And he rejected the paper on the grounds that it wouldn't work, and here's why. And he wrote down the no-cloning theorem. And I have seen his referee report. He genuinely did this. So I say it took 15 minutes. Here's one version of proving it. It's as simple as this. Here's what you want. You want a device that takes an input quantum state that is of some number of possibilities. Let's just say that there are 2 possibilities. It's either psi 0 or psi 1. And there's a piece of tape that's waiting in a standard state. And you want it to take psi sub I, where I is 0 or 1, and the tape prepared in the standard state, and convert it to the original system, and then the tape should have a copy of the quantum state. So this should work if it's psi 0. This leads to psi 0, psi 0. Or it should work if it's psi 1, making psi 1, psi 1. Well, you can't build such a thing if the inner products between psi 0 and psi 1 are strictly between 0 and 1. And the reason for that is unitary evolution preserves inner products. So if you look at the initial inner product of the two possible states, psi 0 and S and psi 1 and S, then because of the property of the tensor product that these things factorize, you just pull it out and it's psi 0, psi 1, and then if S is normalized, then that's equal to 1. So that's the initial inner product. That's what the inner product of the two possibilities would be over here. But after this process, there's two copies. So if you look at the final inner product, it's not psi 0 times the inner product with psi 1, it's that squared. You can't get there by a unitary process, and you can't get there even if you extend the system to larger, a little bit harder proof. But you just can't do it, and it's about that simple to prove it. That's not the actual proof that Wouters and Zurich or Dijks or Ghirardi used. They used one based on linearity. Look at this. We've got one copy of psi 1 here, or psi I. We've got two copies of psi I there. That's not a linear process. You can't take a linear combination of psi 0 and psi 1 and put it in that spot and end up with the superposition here and the superposition there. So that's really what they recognized in about 15 minutes, that it can't be a linear process. Now, actually, this shouldn't denigrate the importance of the theorem, because people had thought about it earlier and had somehow missed the theorem. I give one example that I don't think is very well known. There's a paper by Eugene Wigner, the famous mathematical physicist Eugene Wigner, in 1961, titled "The Probability of the Existence of a Self-Reproducing Unit." And in that paper, he modeled the notion of life by saying that at the very least, life had better lead to reproduction. So he says, it will be assumed that the living state is completely given in the quantum mechanical sense. It has one definite state vector with components vk. Before multiplication, the state vector of the system, i.e. organism plus some nutrients around it, is the state vector phi, which is v tensor w. When multiplication has taken place, the state vector will have to have the form psi, which is v tensor r. That is, two organisms, each with state vector r, will be present, and the nutrients will have diminished. So we've gone from a state from w to r. But the point is, he models the very notion of life by the possibility of cloning. Then he develops a proof that this is exceedingly unlikely that you can find any Hamiltonian that will pull off this process. He says there must be many states, V, all of which represent a living organism. Let us denote the n vectors which represent living organisms by V super k. There was a bad notation here, because these are components and these are different vectors. The index k running from 1 to n. Then every linear combination of vk will also represent a living state. Every linear combination will also represent a living state. But this process that he's calling the reproduction process isn't a linear process. So he should have found the no-cloning-theorem right then and there. And somehow he missed it. Instead, he got a weaker statement that it was exceedingly unlikely. Well, if it's probability 0, which in fact the no-cloning-theorem shows you, then it is indeed exceedingly unlikely. So his conclusion is not wrong, but the steps in the derivation are wrong. Okay, so I promised Flavio I wouldn't talk about the history so much, but you know, it's a little bit of history. What is the importance of this theorem, the No-Cloning-Theorem? I looked up Wojciech Zurek's webpage at Los Alamos National Laboratory yesterday, and I found this line in it. Zurek also demonstrated, so he didn't write this clearly, so somebody at the laboratory wrote it, but it says, Zurek also demonstrated with Wouters that an unknown quantum cannot be cloned. This is a fundamental result of an essential distinction between classical and quantum information. This is an essential distinction between classical and quantum information. It's an extremely important result. Well, it's got 5,000 citations. Well, the importance of it and how essentially different may just depend upon whether you view this state as being associated with the phase space point, or whether you view this as being analogous to the Liouville distribution. In 1995, I was late at night. I was working on my PhD thesis, and I got tired of writing, and I came back to the thought of the lesson of Asher Perez, that we should seek out analogies between quantum states and Liouville distributions. And I thought, if this point of view is ever going to be recognized, we need more examples. So I thought, we need more examples, we need more examples, we need more examples. And I think the thought process kind of went like that. We need more examples, we need better examples. Can we find any better examples? And then I thought, well, Liouville distributions, they satisfy the Liouville theorem. Who knows the Liouville theorem? So the Liouville theorem is that Hamiltonian dynamics, though it may take an area in phase space to a horribly contorted looking thing, so you just draw a circle in phase space and then you see what it evolves to, let's say under some chaotic map, and it may become a horrible, ugly looking shape. But Liouville's theorem says the volume of this is equal to the volume of that. Liouville's theorem. A corollary to the theorem that I had to work out and I didn't know and I hadn't read in the textbooks, but a corollary to the theorem is that the overlap of distinct Liouville distributions is conserved. So if I look at one distribution and I look at another and I look at their overlap, it stays the same. And when I realized that, actually, before I had proven it to myself, I thought that was probably the case. I was like, holy shit, there's nothing quantum about the No-Cloning-Theorem. Everybody has been giving me a load of shit all these years. What's going on is that they're thinking that this is analogous to the point. They're not thinking that this is analogous to the Liouville distribution, because this corollary basically implies there's a classical no-cloning theorem. So let me give you an instance of this. This is meant to be a picture of a pendulum that's swinging, and there are two people out on the other side of the wall, not able to see it. This one says, oh, I don't know the exact variable theta and its momentum right now. 5 minutes.
To the 45.
Oh, I see. Okay, I'm going to get through one example today. Not two. Right. 45 minutes. I'm taking time doing this, aren't I? I should move on. Yeah. So where were we? So here, the one person says, it's, I don't know its theta, and I don't know its momentum. I don't know the angle, I don't know the momentum, but I have a probability distribution for it. It's P0. The other person says, oh, I have different knowledge or different beliefs about that. it's P1. And then there's some system over here that's motionless, and they both agree, oh, this system is motionless. Now we ask the question, is there any physical process, is there anything that we can do to this that afterward will make this person believe that it's P0 times P0 for the two different pendulum? In other words, they're not correlated, but they have exactly the same distribution that they had previously. Is there something that can do that for P0 and at the same time do it for P1? In other words, his state of belief. Can we build some device that will replicate the first observer's state of belief and replicate the second observer's state of belief? Without correlation, because this is crucial actually for the no-cloning theorem. Remember, there's no correlation. It's psi, psi. If you perform a measurement on one and you get an outcome, the measurement on the second one will be statistically independent from whatever outcome you got on the first. Well, the Liouville theorem says you can't do it because the initial inner products will be different than the final inner products, or the final overlap between the distributions, just like in the unitary case. So despite there being a quantum no-cloning theorem, there was a classical no-cloning theorem if you think about Liouville distributions. So I went around the world to the extent that I went around the world back then, and I told everyone about this, and I thought everyone would get excited and say, oh, we've learned something about quantum mechanics. This Asher Perez, he shouldn't be ignored. He's on the right track. Well, that wasn't really the reaction. For example, Ben Schumacher said, oh, fine, maybe that's true. What's more interesting, though, is that classically, you could induce correlation like this. So in the sense that you could do something to the two pendula so that they're doing this, and so the first person's ignorance about this one is also his ignorance about that one. And the second person, his ignorance about this one is the same as that one. In other words, if you perform a measurement on this one, then you know the outcome for that one. So there's correlation now, but in a sense there's cloning, because it refers to the cloning of the phase space point. So this led to maybe a more refined question. Is there something that you can't really do quantumly, even with states of knowledge, that you can do classically? This led to something that we call the no-broadcasting theorem. So here's a generalization of no-cloning. The idea is that we've got two possible quantum states. We're going to drop one of them into the magic quantum trousers. And out of the trousers will fall two quantum systems. And we want it to be such that if we throw rho 0 in here, we get a state down here between the two systems, possibly entangled, that I'll call rho 0 tilde. The defining property of rho 0 tilde is that if I throw this system away, I've blackened the bucket, then what's left over here is exactly what I threw in. If I throw this system away, then what's left over here is exactly what I threw in. Okay, so there's this partial trace property that I have to reproduce the quantum states individually, but there might be correlation between them, or there might be entanglement between the systems. Can I do that? Generally. I want to be able to do it for rho 0 and rho 1. If I had thrown rho 1, I would have rho 1 tilde, and then rho 1 and rho 1 in those spots. Can I do it generally? Well, the pendulum show you that you can do it when states are commuting. If they're commuting, then they can be simultaneously diagonalized, and you can think of the diagonal elements as being probabilities for something that is already there, something that is existent, like the classical phase space point. So this state represents some bodies state of knowledge about what ball they will find when they lift off the top of the bucket. Similarly, this one, but a different state of knowledge. Well, you can see that you can just do the thing that I told you, namely, you reach in, you look at the ball, you reach in another pile, and you pull out a ball of exactly the same color. Now, the person on the outside, his knowledge of this one will be the same as his knowledge for that one. But if you reveal the color of this one, it'll also reveal the color of that one. So more formally with quantum theory, you can see that you can do it. I've got two commuting density operators here. This is the diagonal basis. And you just make some unitary operation that makes a copy of whatever B is. And so you end up with this kind of quantum state. So you can do this broadcasting process with two commuting density operators. But what are the necessary and sufficient conditions on the two states, row 0 and row 1, so that you can do it? Well, you have to think about that. You can do it when they're commuting. Guess when you can't do it? When they're non-commuting, or at least that was the guess. And the reason for the guess was the things that we had learned from Asher-Perez about Cauchy-Specker theorems, that if you have a more complicated set of observables, not just one in the diagonal basis, but a more complicated set, then there's no way to ascribe a pre-existing value, in a non-contextual way at least, to some value that's already existent before the measurement. So we thought, oh, the reason you can get broadcasting when they're commuting is because you can act as if there is a value there. Let me say it just louder. You can act as if there's a value there. But if they're non-commuting, then there's no mutually diagonalizing basis, and you can't act as if there is a value there. So how do you prove it? Well, it wasn't immediately obvious. And it also wasn't immediately obvious that that was the answer. This was a 6-month process. First thing we needed was some kind of machinery to put in place of the overlap that we used for Liouville distributions. So that led to an excursion on how to get a good notion of overlap for quantum states. One obvious idea is to just say, if I introduce a measurement, my two different quantum states will give rise to two different probability distributions. And I can look at the overlaps of the probability distributions, and that will give me a measure of how much overlap is on the quantum states with respect to that measurement. But you got with respect to that measurement. Well, maybe a good measurement is the one that minimizes their overlap, and then it tells me something intrinsic about the quantum states. So that was the kind of machinery that we needed. The question is, what measurement minimizes these things, minimizes the overlap for these two quantum states? And that took some math. All right, so here's the main thing I want you to take away from this slide. We wanted to generalize the Liouville theorem to quantum states so that we could make a foundational statement. Foundational statement being that this thing corresponds to that. It doesn't correspond to that. So you play around with the matrices. You recognize that these are positive semi-definite matrices. You can take the square roots. You use the cyclic property of the trace. You use the Schwarz inequality, blah, 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 blah. You put it together, and you get a lower bound on this number, the overlap, lower bound for all possible measurements. And then there's a parameter that you can throw in so that you can tighten up the overlap. And in fact, you can show that the minimal value of f is this thing, with equality achieved by a suitable measurement. So what this gives us is a notion of overlap for quantum states that's really ugly, mathematically ugly, one might think. It's the trace of the square root of the square roots of the products of density operators. Doesn't look all that pretty. But it's got a number of wonderful properties. For instance, it's bounded between 0 and 1. It's 0 if and only if the two states are orthogonal to each other. It's 1 if and only if the two quantum states are identical. It's symmetric in 0 and 1, despite the fact that it doesn't look like it's symmetric in 0 and 1. It's invariant under unitary operations. When we have tensor product states, it factorizes. And it has an all-important property that I call the partial trace property. The partial trace property is, if I've got a quantum state on a large system, two possible quantum states, rho s of the two systems F and G, and S can be 0 or 1, and I throw away one of the subsystems, then the distinguishability decreases. In other words, the overlap always increases if you throw one system away. So I had that very nice property. So with that piece of machinery in place, go back to the task of broadcasting. There we've got an input quantum state. It can be rho 0 or rho 1. We've got a piece of the machine, a tape, that's prepared in some standard state. And then we've got some environment that it interacts with. And if I take my environment large enough, I can think of that as a unitary interaction. So these quantum systems become coupled through a unitary interaction. And when I throw away the environment, I should be left with a quantum state on my systems A and B that is of this form. If this is rho 0, this will be rho 0 tilde. If this is rho 1, this will be rho 1 tilde. That's what we're going to do for cloning. But now look at what the partial trace property leads to. It leads to this, that in this process for making the broadcast states, well, the initial overlap is equal to this overlap, and that overlap is equal to this one with a unitary operation thrown in. But then we take a partial trace, so that means we get this inequality and we get that. So it says distinguishability cannot increase. In other words, overlap can never decrease. So let's go back to broadcasting. We wanted a state such that the partial trace on both sides gives me the input quantum state. But then because of this, what did I call it? PTP, I forgot what PTP stands for. Partial trace property. Because of the partial trace property, we get a decrease there, and we get a decrease there. The upshot of it is, if you want to be able to broadcast, then it had better be the case that the initial distinguishability between the states and the things that they evolve to have all got to be equal. You can study the optimal measurement that gives rise to that, and then you really do the hard mathematics. And you extract from that that can only occur if and only if, it can occur if and only if the two states commute. So in other words, in those cases where you can act as if there is a value existing before the measurement, then you can broadcast it. But in those cases where you can't act as if the states are non-commuting, then you can't broadcast. So that was going to be one of my examples of the workaday quantum information theorist. And I think maybe let me just make this point. I'm not going to give you the second example. It would have been related to this, that a wave function is not something which exists in nature. And squaring that with the phrase that we always use in quantum information called the unknown quantum state. You teleport unknown quantum states. You try to error correct unknown quantum states. You do lots of things with unknown quantum states. But if quantum states are someone's states of knowledge, what can it mean to be an unknown quantum state? It's always known. It's known by somebody. So what do you mean in these protocols? That was going to be the second one. But let me just conclude by saying the import of the first one. Let me go back to this slide. What I think has been interesting about quantum information is that one could be working in quantum foundations in such a way that unless someone else is foundationally minded, they wouldn't even know that you're doing that. So how did we sell this paper? We said it's important for understanding eavesdropping protocols in quantum cryptography. And that was true. So that's where it gets its citations from. So here's a nice thing about quantum information that I think makes it unique, particularly as a point of discussion for this conference, is that the field of quantum information provided some of us with a kind of cover. We could be doing quantum foundations in the closet, so to speak. We never had to declare ourselves in the open. We didn't have to declare what we really were. And that was a nice opportunity. And it goes back to the founding fathers of quantum information, who are now, for the most part, forgotten, who themselves were thinking about foundational things and realized that this thing is not about a state of reality, but that this thing is rather, should be thought of as a state of information, and therefore the phrase quantum information. Thank you. Sorry to have gone over time.
We are going to take just 5 minutes for a question. Please just focus on clarification question about the talk, not the general context. And we will have plenty of time, half an hour discussion after the second tandem talk for the more conceptual questions.
So I have a question about your interpretation of the no-broadcasting-theorem. So the conclusion that you get that the states must commute is not the same thing you would get if you were trying to look at sort of sub-theories of quantum theory, like Clifford theory or Speck's toy model or something like this, which I assume you would be able to do broadcasting in the right, you can have something that is not just commuting quantum states and that can still be interpreted like under a non-contextual hidden variable model.
No, in those cases, you can't broadcast still, even though you can act as if there is an existing value. So good examples come from the Speck's toy model, where from the very outset there is a state of existing reality, but you just don't know it. And there's something about the theory that blocks you from it. So we didn't realize that at the time. So I'm glad you asked this question. So at the time, we thought we had walked away with a characterization that was essentially conveying the same physics as Cauchy-Specker, that without performing the measurement, the value doesn't exist. So when you've got non-commuting things, you cannot act as if there's something there. What the toy models then later taught us is that you can still act as if there's something there that can be broadcast, even in theories, you can still get a no broadcasting theorem in some theories where it is assumed at the outset that the value exists, but there's something that blocks you from ever knowing it. So when I had shown this picture, and I said, of course you can do it when they're commuting, well, that is an example in quantum theory. When they're commuting, you can say, well, I'll just look at what's in the one bucket, and I'll just say, oh, it's blue. Let me pull a blue one out of my pocket, and now they're correlated, and I have broadcast. You know, send the two blue balls out. But quantum theory has the feature that you can look at the value that's assumed to exist in that case. In other toy theories, you still can't get the knowledge of it, so you couldn't do this because there's some limitation. So in those theories, there is a no broadcasting theorem. It shows that this wasn't as powerful a way of thinking. But I had to give a talk on something, so I...
Chris, there's something I'm missing from the beginning. If you have a state psi, it implies that there's an uncertainty principle between P and Q. So how can you how can you connect it to one point P and one point Q in the phase space?
Well, you can't exactly. No, this was always meant to be an analogy. Now, what we've done in the years since is you can introduce a quantum measurement that is, for instance, an attempt to measure P and Q simultaneously, but that measurement has certain characteristics. So, for instance, the coherent states, you can think of that as a measurement that's an attempt to measure P and Q at the same time. You still get an uncertainty principle for P and Q. But anyway, you can try to treat that simultaneous measurement as a state of pre-existing reality, and things go wackadoo. They don't work. But the example that I showed here is, so it's not really a phase space. This is a classical probabilistic thing. It's just I am in one of, there's some basis. Let me do it this way. And I am in one value, one element of the basis, this orthogonal basis. I'm in one of these. I don't know which one. And we know that we can perform a quantum non-demolition measurement to find out which one and then make a reproduction of it. So it's really, I'm not talking about a phase space here. I'm just talking about an orthogonal basis. And that can be broadcast. If you wanted to try to broadcast position and momentum simultaneously, that one you can't.
Okay, so let's thank Chris again for the wonderful talk.